Hi, I'm Alfonso Algares, and in this lecture I'll be covering velocity and acceleration on rigid bodies. First, I'll go over the concept of reference frames and their properties, which are critical to understanding velocity and acceleration on rigid bodies. We will then look at differentiating functions in relation to different reference frames, and more importantly, how the derivative of a function in one reference frame relates to a derivative in a different reference frame. We will then look at the application of these concepts to the case of rigid bodies, where we will be using them to find the velocity and acceleration of points, or the angular velocity and acceleration of the body as a whole. First of all, what is a reference frame? Generally speaking, a reference frame is a set of vectors that span the entire vector space, meaning that linear combinations of the three vectors can represent any other vector. Rigid bodies can serve as reference frames, and reference frames can be treated as rigid bodies, a useful fact when dealing with the dynamics of objects. Cartesian reference frames are a subset of these reference frames which meet a series of conditions. They are right-handed, meaning that the third vector that comprises them is the result of the cross product between the first two, and that these three vectors are also mutually perpendicular, meaning that they all form a 90-degree angle between each other. They are also usually expressed as unit vectors with length 1. Some Cartesian reference frames are inertial. The reference frame is not accelerating with respect to other reference frames. Reference frames do not change vectors. What reference frame you choose to express the location of a specific vector is not important. However, reference frames do change the derivative of vectors. When differentiating in a reference frame, we need to be mindful of whether a reference frame is inertial or non-inertial, because the resulting expression will be different. If inertial, the derivative will treat the unit vectors as coefficients, but if it's non-inertial, the unit vectors are changing, and thus they need to be included. Using these expressions, we can find an expression for the derivative of a function in a different reference frame. Remember, though, that these two reference frames might be moving in relation to each other. This means that we cannot treat both as inertial, but we can treat one as inertial and the other as non-inertial. Setting the expressions for the inertial and the non-inertial reference frame equal to each other, we can group up the terms depending on what they represent. The terms on the left represent the inertial frame of reference we are finding our derivative in, and the terms on the right that are not derivatives of our unit vectors represent our derivative on our current reference frame. The other terms that do depend on the change in the unit vectors of our reference frame are the results of rotation. We can also express these terms as the cross product of the angular velocity of our current reference frame and our original reference frame. This simplifies the expression to this form, which turns out to be an extremely useful relationship when dealing with rigid bodies. This expression is true for any vector when changing reference frames. We can now use this newfound relation to understand the velocity of different points on a rigid body. First, it is important to understand that velocity and acceleration actually mean when dealing with rigid bodies. Points on the interior or surface of a rigid body have velocity and acceleration, but as they are treated as infinitely small points, they cannot rotate about themselves, so they do not have angular velocity and acceleration. The entire rigid body can rotate about itself, so it does have angular velocity and acceleration, but as we are using it as an inertial reference frame to perform our calculations, it does not have velocity or acceleration. This does not mean that the rigid body itself does not move in space. It simply means that it is not moving in relation with all the points it is in or on its surface. The insight that allows finding the velocity of a point on a rigid body comes from treating the switch in position as a switch in reference frames. Using the expression we found before, we can use the change in position as our vector and thus find an expression that relates velocity at the new point to the velocity at the starting point, plus the cross product between the angular velocity of the rigid body and the displacement vector between the two. Using this expression, any unknown variable can be found if the other three are already known. Dealing with acceleration involves taking the second derivative of the position of a point in a rigid body, which will require some known derivation rules. Most importantly, the derivative of the cross product is the derivative of the first term cross the second term, plus the first term cross the derivative of the second term. Using this known rule and the expression we found for velocity at a given point, we can further derive to find an expression for the acceleration at a given point. This acceleration will be equal to the acceleration known at a previous point plus two other terms, resulting from the cross product of angular velocity and displacement. The first term is the cross product of the derivative of the angular velocity, angular acceleration, and the displacement vector. The second term is the cross product of the angular velocity and the derivative of the displacement vector, the velocity of the initial point. This can be expressed as the cross product of angular velocity and displacement, which yields this final expression. Using this equation, the acceleration of any given point on a rigid body can be found given the acceleration at an initial point, the displacement vector between the two, and the angular velocity and acceleration of the rigid body as a whole. To recap, when dealing with a rigid body problem, it is imperative that you understand that points have velocity and acceleration, while rigid bodies have angular velocity and acceleration. Using these two expressions, you will be able to use your initial values to find any other unknown variables at any point on your rigid body. And using this more generic expression, you will be able to express those known values in any reference frame. Finally, in order to understand how we can apply these concepts to the aerospace field, let's consider the case of a satellite orbiting Earth. This satellite has spun out of control and is spinning at pi over 3 radians per second. Now, this is a communication satellite, so the antenna sits 3 meters above the center of mass. What we want to know is what is the speed at the tip of the antenna, and will the antenna break if it cannot withstand more than pi squared meters per second squared worth of acceleration. Well, using the equations we've discussed before, we can very quickly calculate the velocity at the tip of the antenna. As we're considering the velocity in relation with the center of mass of the satellite, the velocity at the origin, v1, would be 0. And so we're only left with the angular velocity and the displacement vector, which would come out to be pi meters per second. And for the acceleration, we have no acceleration at the center of mass. We also have no angular acceleration because it's spinning at a constant rate. So we're only left with the last term, which comes out to be pi squared over 3 meters per second squared. So using the relations we found, we can tell that the satellite will be fine, even though it's spinning out of control.